I didn't record that part. Sorry, guys. So we go back to the app, right? The other parameter that you can change is the non-ideal parameter, right? That is just a parameter to show how ideal or how non-ideal it's that particular solution. If you see, we don't have a specific component, right? We only have component A and component B, and that's it, right? So we can change this value, and depends on the solution, depends on the affinity of those or of the mixture. This is going to behave more closely to an ideal solution, right? In that case, well, the partial molar enthalpy, well, or the plot of the enthalpy is going to be a straight line, right? That has a slope, and that's it, right? And of course, the partial molar enthalpy is going to be the enthalpy of the component, and that's it, right? And if we change the non-ideal parameter to the other side, of course, we're going to have a plot in the other way, right? It's going to be more like a parabol inverse instead of the inverse parabol, right? Okay, so all the properties, all the partial molar properties changing more or less in this way. Depending on the mixture, is going to be closer to ideal or further apart from the ideal case, right? For example, if you have components that have a very close relation, for example, methanol and propanol, that they are molecules that are very well, the structure is almost the same and the properties don't change that much. Well, then the partial molar enthalpy would be more or less in an ideal case, right? If you have substances that they have a different structure and they have a behavior, well, they will have a behavior that it's way different from the ideal case, no? Like in this parameter, if we use this parameter in 15 instead of 0, 1, right? Okay, so yes.
So we decide the ideality of the parameter. We have like to investigate and we put the number, or
No. Okay, no. In this case, we are only changing the parameter to see how an ideal solution would behave and how a non-ideal solution would behave, right? Each pair of substances, they're going to behave completely different, right? This is a general simulation, let's say, like that, right? It's not a specific pair of components. Yes. If we have a pair of components, then this parameter doesn't exist, right?
Yeah.
Just a model, right? Model the ideal or non-ideal solutions, right?
Okay.
Okay, so we're going to use a couple of the partial molar properties in another class, but in a schedule for later on, right? So we're going to continue to the vapor liquid equilibrium. So what do you any of you what do you understand for a vapor liquid equilibrium? If anybody can unmute your microphone and answer, please.
Well, I think vapor liquid equilibrium is a state where you can find both phases in in the same system. I mean, that's what I understand.
Yeah, okay. So you have a liquid phase, right? But you in the gas phase, you have a vapor in it, right? Like for example, water in the atmosphere, right? If you have a pond of water, you will have water, well, liquid water, of course, and part of the water in vapor phase, right? So yeah, something like that. So for example, here we have a couple of examples that are interesting. For example, this one. Sorry, what is it? A soda can, right, or a Coke in this case, right? Inside of that particular can, well, you have a liquid. You have a liquid, and you have a gas that is dissolving it, right? And in the empty, well, not in the empty space, in the gas part of the system, you will have a vapor that is going to have CO2, right? And a little bit of air or a little bit of water, right? Depends on the the behavior of that particular system. For example, what do you expect that the gas phase would be more water than CO2 or more CO2 than water? Assuming that we only have water and CO2, of course. So which one is more volatile, the CO2 or the water? Jose, you
CO2?
The CO2, right? So the CO2 is it's a gas, right? Well, it's in gas form at 25 degrees and 1 atmosphere, right? And water, well, it's liquid, right? So that gas phase should be more CO2 than anything else, right? Okay. So something like that for any system, you can see more or less the behavior just by looking at the substances that you have, right? Another example could be, for example, a perfume, right? In a perfume, what you have is, well, you have a very volatile solvent, and then you have some molecules that give the smell to it, right? So again, if you have a bottle with half of perfume, the gas phase is going to be in equilibrium, right? You're going to have the solvent in the liquid phase, but you're going to have solvent in the gas phase too, right? As other components like water, for example, right? Another one could be more close to engineering, to do a distillation, right, or to do a flash distillation, that you have different vapor pressures or different boiling points, and depending on those boiling points, you can separate those mixtures, right? And those mixtures, you can separate them by well, heating the solution and then condensing that gas, right? The gas is going to have, well, for example, if you do a distillation of methanol or ethanol and water, what you're going to find is that the first part of the distillation is going to be, of course, almost all ethanol. We're going to have a minimum amount of water that goes into the equilibrium, right, into the gas equilibrium, right? So that's why, for example, if you want to purify water, for example, you need to do more than one distillation, right? Because there are equilibriums in the vapor-liquid equilibrium, right? So if you have an equilibrium, you're going to have a little bit of each one, and we need to know how to process the distillation, or how to do a flat distillation as efficient as it can be done, right? Depends on the mixture of the compounds. Another one, for example, that is very important for divers, for example, is the nitrogen in the blood, right? Depending on the pressure and more than pressure than the temperature, because the temperature is almost constant in the body, but the pressure depends on the pressure of the gas. That gas is going to dissolve more or less. And if you have a higher pressure, like when you are at 30 meters underneath the water, well, you're going to have a higher pressure, and then the nitrogen you're going to have more nitrogen dissolved in your blood. So if you go up to the surface, that pressure is going to be reduced, and then the nitrogen is going to go to gas phase, right? And if that happens, of course, you end up with nitrogen in gas form in your joints, and that can lead, for example, to a bone to break, right? So that's one of the cautions that many divers should have, right? And that's why they have to climb up slowly, do a safety stop, and so on. I don't know if any of you dives, but that's a usual plan of diving, right? You go to the bottom, and then you have to start climbing up slowly, and then you do a safety stop. And the safety stop is exactly to prevent these kind of things, okay? For the nitrogen to form bubbles and to crush your joints in a couple of years or something. Depends on the amount of nitrogen, of course. So that's a couple of examples. I'm going to put a video, right? That it's a YouTube video. I hope you can see it as well as I do. It's a video of crash course. It's a web page. I think you know it already. It's about partial pressure and vapor pressure. Okay, it lasts 12 minutes. We will see a couple of things afterwards. Okay. So let me play it for you.
Imagine, if you will, a state dinner at the White House. These are not small, intimate affairs. 300 or so adults mingle in close quarters, yet somehow it's a quiet gathering where people behave gently, move around slowly, and almost never run into a wall. However, as a group, they do take up a lot of space, they give off a lot of heat, and lots of things get moved around. In these ways, the room is changed by their very presence. Now picture a 5-year-old's birthday party. Very different situation. You would not call that quiet or formal. But that is not enough. Imagine the most popular 5-year-old in the world, his birthday party. 300 kindergartners in one room for several hours, shoving each other, running like crazy, and definitely banging into walls. Their bodies are smaller, but because of their faster motion, they collectively take up just as much of the room and give off just as much heat as the slow-moving adults do. And things get shoved around just as much. Now imagine we have a surprise for those 300 adults at the state dinner, all very formal and tucked in. There are 300 5-year-olds in the next room, bouncing off the walls, and suddenly we drop the wall. Excellent. First of all, those kids are going to run all around the room, squeezing in between the more sedate adults. That will cause the adults to move apart a little, maybe even bumping into a wall now and again. But because the adults are moving more slowly, they'll get in the way of the kids running and slow them down some. That might even cause the kids to run to the walls a little less often. The most important thing here is that the overall bouncing against walls will be equal to the bouncing of the adults plus the bouncing of the kids when they were in separate rooms. And you will not be shocked to find that we are currently in amongst an elaborate analogy to do with gases. It shouldn't surprise you to learn that this particular party was started by John Dalton, the English teacher, the science teacher from England. He wasn't an English teacher, he was English, who in 1803 was the first person to use real science to figure out what atoms are and how they behave. His theory included a few misconceptions, but it contained enough facts to be super useful. Dalton's atomic theorizing began when he expanded French chemist Joseph Louis Proust's law of definite proportions to develop the law of multiple proportions, which says elements combine in simple whole number ratios of their masses. But here's the cool part. That exact same research also led to an important gas law. Dalton studied gases basically by mixing them together. He was measuring how much of one element would react with a given amount of another, but as he mixed those gases, he noticed something else. The total internal pressure of his container was always equal to the sum of the individual pressures of the gases that he had added. Upon recognizing that this happened every single time, no matter what gases were used or what amounts were added, Dalton stated his discovery as the law of partial pressures. As long as the gases don't react chemically, the total pressure exerted by a mixture of gases is equal to the sum of the pressures that the individual gases would exert if they were alone. Here's an example. Scuba tanks often contain a mixture of oxygen for breathing, obviously, and helium, which helps prevent decompression sickness because it's released from the blood more readily than nitrogen and air. That allows divers to return to the surface more quickly with less risk of gas bubbles forming in their blood. We're going to use some approximations here, so don't yell at me if you know exactly how big this tank is, but we're going to say that it's 10 liters. And we'll say that it contains 4 moles of helium and 1.1 moles of oxygen gas. The temperature in this room is about 22 degrees Celsius or 295 Kelvin. So, what's the total pressure inside the tank? In order to solve that, we need to know the pressure exerted by each gas individually, and we can find that with the ideal gas law. Starting with the helium, we don't know the pressure, so we're solving for P. The volume is 10 liters, and we have 4 moles of helium. R is always the same, and the temperature is 295 K. The calculation should show that the helium would have a pressure of 980 kilopascals if it were alone. Now for the oxygen, all the numbers are the same except for the moles, which is 1.1 for the oxygen. According to the calculation, the oxygen alone would have a pressure of 270 kilopascals. The law of partial pressure says that the total pressure is equal to the sum of the individual pressures, so in this case 980 plus 270 equals 1,250 kilopascals or 1.25 megapascals. Easy peasy. This additive property of pressures is closely related to the fact that mixing gases combines their particles, thus increasing the total moles of gas present. The ratio of moles of the individual gases in a mixture to the total number of moles is called the mole fraction. And of course, mole fraction gets to have its own little esoteric symbol to represent it. The lowercase Greek letter chi. Chi sub 1, the mole fraction of an individual gas, equals n sub 1, the number of moles of that gas, divided by n sub total, the total number of moles in the mixture. And because the total number of moles is the sum of the moles of all the gases, we can also say that chi sub 1 equals the moles of any one gas divided by the sum of the moles of all the individual gases. You see how that last formula looks a lot like the one for partial pressures? That's because they're basically the same thing. Through the ideal gas law, the number of moles is directly related to the pressure a gas exerts, as long as the volume and temperature remain constant. So you may have figured this out already. Rather than having to calculate individual pressures first every time, as we did with the scuba tank, or calculate the individual moles in the opposite situation, we can often calculate what we need directly from what we already know. Let's give it a try. The air that we breathe is about 21% oxygen, or 21 parts oxygen in 100 parts air. What is the partial pressure of O2 in the air at a total atmospheric pressure of 97.8 kilopascals? We can substitute moles for parts and use the mole fraction formula to solve this problem. Plug in 21 moles of oxygen for the individual gas and 100 moles of air for the total amount, then put in the total atmospheric pressure, 97.8 kilopascals, and do the equation. With correct rounding, that'll give you a partial pressure of 21 kilopascals for oxygen. Sometimes, however, gases mix together in ways that aren't so predictable. For instance, one way to collect a gas is by bubbling it through a column of water to trap the gas at the end of the column. This is called collecting a gas over water. The only problem is that liquid water constantly is giving off a small amount of water vapor. That's why if you leave a glass on a desk for long enough, there will eventually be no water in it. There are always going to be a few molecules that have enough kinetic energy to escape the liquid. The amount of vapor that's released depends on the temperature of the water. The more heat energy it has, the more vapor we get. Like all gases, the water molecules move around a lot and sometimes bump into the sides of the container, thus creating pressure. This is called the water's vapor pressure. The water molecules mix with the gas that's being collected, and when that happens, as good old John Dalton taught us, total pressure in the column equals the pressure of the collected gas plus the vapor pressure of the water. So, to know how much gas we really collected, we have to subtract the vapor pressure of the water from the total pressure. This gives us the pressure exerted by the collected gas, and from that, we can calculate the moles of gas present. Here's how it's done. Here I have a tub of water and a graduated cylinder that I've put into the water and then filled with water, so now you can see it's got no gas in it, just water, and we are going to capture gas in here and see how much gas we capture. Here I have a bottle and it's sealed with this little tube. This is the only way for gas to get out of here, and in here right now I have vinegar, an aqueous solution of acetic acid. This is baking soda, more properly sodium hydrogen carbonate or sodium bicarbonate. I think we all know what will happen when this comes in contact with vinegar. Now, to prevent that from happening before I want it to happen, I made it a little boat for it, and the boat is theoretically, I hope, going to sit on top of the level of the vinegar and float there without spilling. Yeah, I did it. Before the big action scene, let's talk about what's actually happening, chemically speaking, because as you know, I love to speak chemically. The acetic acid and sodium bicarbonate combine to form sodium acetate, carbon dioxide, and water. The sodium acetate dissolves readily in water and will stay that way. The carbon dioxide, on the other hand, is the source of all our fun. It's a gas, and it forms so many little bubbles in the surrounding liquid that it's almost a foam, expanding quickly and dramatically. As the carbon dioxide escapes through the foam, it goes through the tubing and bubbles through the column of water, so we get double the bubbles, double the fun. And don't forget, at the end, we'll be able to calculate how many moles of CO2 are produced by this reaction. Let's get to it. It's going to take more than two hands to do this, so I have a lab assistant with me here today. This is Michael Aranda. All right, Michael, put the tube into the cylinder there, and I get to do the fun part, which is to shake this and make bubbles. Bubbles! A little more. So we have collected exactly about almost exactly 90 milliliters. So like 90.5 milliliters of carbon dioxide. You can go away now. We also know, because I know, that the atmospheric pressure is 101.8 kilopascals. Remember, we also need to know what the vapor pressure of the water was that we have to subtract. The amount of vapor pressure that water gives off depends on its temperature, and there's a table we can look at, and if the water is at 19 degrees Celsius, according to the table, the vapor pressure is 2.2 kilopascals. So now finding the pressure of the carbon dioxide alone is easy. We simply subtract 2.2 kilopascals from 101.8 to give us a pressure of 99.6 kilopascals for the carbon dioxide. Finally, we have to make sure that the pressure inside the graduated cylinder is the same as the atmospheric pressure, and to do that, we just have to make sure that the levels of both of the liquids are the same. And doing that, I can see that it is almost exactly 90 milliliters of carbon dioxide in the cylinder. Now we plug everything into the ideal gas law. P is 99.6 kilopascals, V is 0.09 liters, N is what we're trying to find, R is always the same, and the temperature is 292 Kelvin. One quick calculation and we find that we have collected 0.0037 moles of CO2. At a molar mass of 44 grams per mole, that's 0.16 grams of carbon dioxide. I am excited by our success here. That might not sound like a lot, but collecting a fairly substantial amount of gases and being able to make accurate measurements of them with a simple apparatus like that is pretty impressive. For me, it sounds like time for party. Thank you for watching this episode of Crash Course Chemistry. If you weren't late to...
Okay, so that was the video. Of course, information that you already knew, right? But I needed for everybody to have the same information, right? The actual thing is to understand that there is an equilibrium between different phases, right? Between the liquid and the gas. So we're going to start seeing what are the VLE diagrams, that are the vapor-liquid equilibrium diagrams, right? Okay, so I'm going to start with the one that is more complex, and then we're going to see the ones that are not so complex. Okay, so here in this plot we have three different axes, so we have a three-dimensional picture or diagram. So in this part we have the molar fraction and the vapor molar fraction of a component. So X and Y1, right? So 0 is over here, and then the 100% of it, of X, of O1, is that one, right? Then in the other axis we have the temperature that is going from low temperature to high temperature over here, right? And in the other one we have the pressure. And the pressure, again, we start in low pressure underneath, and we go to high pressure over here, right? Okay, so pretty straightforward. So then let's see what is this, what's all this about, right? If you have any questions, please unmute your microphone and interrupt me at any time, okay? We're going to focus right now in this pane. Let me see if I can correctly plot it. It's, let's see, is image. Okay, so looking through this window, right? That window that will be the diagram of X, well, the P, pressure, versus the molar fraction. Yep. Okay, so if you see that, we are going to have different temperatures, right? A low temperature and through a high temperature. But we have to choose one temperature, right? Because we can't have all the temperature at the same time because we can't see anything, right? So we'll choose, let's say, whatever the temperature that it's in D. Okay. Here, the temperature in D. Okay. So we're going to make a cut of this volume. This volume, the gray volume that we have all over the image, is where the equilibrium of vapor and liquid are, right? In all the other parts, in all the white space, let's say, we only have either a liquid or either a vapor, and that, or a gas in this case, right? And in the gray lobe that it's all this from K to C2. Here from K to C2 to all the way up up there through the curve to S to C1 and so on, right? All this volume, all that volume. Well, the volume is where the vapor and the liquid are at the same time, right? Right? At the same moment. Okay. So the first thing that you need to see is that if we do a cut like that, we're going to have this volume over here. I'm going to try to draw a little bit so you can see it perfectly, right? So we have that area over there. Okay, so if you're underneath that area, you should have what? A liquid or a vapor? You should have a vapor, right? Because you have a low pressure, right? We are underneath the plot, so here we should have a vapor, right? Underneath the volume that I just wrote. And in the at higher pressures, we should have a liquid, right? Yeah. So if you have a vapor underneath and a liquid up there, this line from A, right, to B let me change color so I can draw it. This is not going to be a perfect drawing, by the way. I'm not very good at drawing. So this line over here, there you should have a saturated liquid, right? In that particular line, the first bubble or the first gas is going to form. That is the bubble point of that particular substance, right? Or if you have the lower part, the lower line, it's going to be, of course, the dew point, right? Let me arrange for you. That was horribly done. Horribly done. It's not easy to draw in these kind of things. But okay, that particular line should be the dew point, right? Where if you have a vapor, if you have a gas, you're going to augment the pressure until you reach that particular line, the yellow line, and there the liquids start to form, right? So you start to form the first drop of liquid, okay? And all the other part, well, in there you're going to have an equilibrium of vapor and liquid, and you're going to find different proportions of it depending on the conditions or on the interactions between the two substances. Okay. Yep. Do you have any questions about this first part of the diagram? Yep. Okay. So if you follow this, let me see, where is my mouse? If you follow this lobe over here, this part, okay, whatever you have up here in this yellow line, this yellow area that I'm going to draw here, you're going to have, well, this is the critical point of the substance, right? So after that area, you're going to find, this is the critical point of the substance. So you're going to find a gas, right? You're not going to find a vapor anymore. So if you have a superheated gas, so you can't condensate it, right? And you can condensate it because there is no equilibrium between the different phases, right? So you're going to find, well, after the critical point, you will find a gas, right? You can't condense that. You have to lower the temperature to obtain, again, an equilibrium from a phase, okay? Okay, so another couple of things. If you follow this line, let me, okay, if you see the point A over here on the left, okay, the point A, you only have the component 2, the component B, or whatever you want to call it, right? So if you follow that line from E here underneath E, and you start raising the pressure, you're going to find that you're going to find a temperature. Well, you're going to find a pressure where the vapor changes to liquid, right? If you have pure substance, that's the boiling point of it, right? That's the temperature at which the substance changes phases, right? And it's only 1 point. But if you have a mixture, if you have a mixture, you're going to have well, a difference in those temperatures, right? From the dew point temperature and from the boiling point temperature, right? And in there you're going to have the equilibrium. Again, if you go to B, you're going to have the same thing, right? Now you have the component 1, the component 1 in pure form. So you start in D, where is it? If you start in D, in point D, and you start raising the pressure, you're going again to find pressure where the substance changes to liquids, right? Okay, so all that is if we look only to the pressure and to the fraction of the substances, right? But what happens if we have a constant pressure? That's more common to have, right? We have a constant pressure all the time here in Mexico City, and we know whatever you want. So let me erase all this, leave it in. Okay, so now what you want is a constant pressure, right? A constant pressure. We're going to use a constant pressure, like so. Color. We're going to have a constant pressure that is going to be this pressure, K, right? The constant pressure at the point K. Right? So this time around, if we want to have a constant pressure, it's like if we're seeing the diagram from the z-axis, right? From here down there, right? We want to see we want to see the fraction and the temperature, how those changes, right? And if we do that, what you are going to find is this area over here. And if you see you have something similar, or you have a shape similar to when we had the constant temperature, right? You have something very, very similar. But the only thing that changes a little bit is how you find the pure substances, right? So the pure substances is going to be on the point K, on point H. Those are the pure the pure substances, right? And there you will have the boiling temperature or the boiling point temperature, right? At that constant pressure, right? Any questions about it? A moment. Okay, so now I'm going to draw something similar to see what is going on with the different phases that we have, right?
Teacher, and here also the line that is in the up is the saturated liquid, and the one down is the one of the vapor.
I'm going to that part exactly.
Okay.
So we have in this diagram we have the lower part of the plot, more or less like this one. It's at a low temperature, right? You have a lower temperature in this side, right? So if it's at lower temperature, this part, where's my mouse? There should be then a liquid, right? Because you have, well, if you have a lower temperature, you're going to find condensed phases like liquids, or if you follow that trend to lower temperature, you're going to find a solid, of course, right? And then in the upper part, of the plot, now it's this one, lousy drawings, you're going to have higher temperatures, and if you have higher temperatures, you should have a vapor, right? Yeah, does that answer your question? Mm-hmm. So again, if you go from a lower temperature to a higher temperature, you're going to have a mixture with a defined composition, and then you're going to get to this line, to the equilibrium line, and there you're going to start seeing the first bubble of gas, right? If you continue, you're going to have a mixture of vapor and liquid, and then if you continue, you're going to get into the line where you find the first, you start to see only vapor, right? If you go from the other way around, if you have a higher temperature and you go to a lower temperature, you're going to have a gas with a known composition, and then you're going to start seeing the first bubble when you touch this line, right, at that particular temperature, and then you're going to find again an equilibrium from vapor and gas, right, and then again to liquid and so on, right? So if we want to separate a mixture, of course we can't separate it without going into the vapor liquid part of the plot, right? We need a pressure and a temperature that gives you this in this area of the plot, right? Any area of this three-dimensional space, okay, of course, but we usually do it at constant pressure, right? So, any questions about this diagram, guys? Is it clear? Yeah. Okay. So this is the whole thing, right? But it's very uncommon to work in a three-dimensional plot because they are very difficult to work with. So we usually work in two-dimensional spaces. Okay. So what we're going to have, there can be more, of course, more different diagrams, but the more common is the temperature XY diagram and the pressure XY diagram, right? At constant pressure or at constant temperature, right? So we're going to see another one of the apps that is the one that says, what happened? This one, right? Sorry, no. Here it is. Okay, so this app, right? So if you open this up, is the one that it says PXY and TXY diagrams for vapor liquid equilibrium. You're going to find a plot like this one, right? In this particular case, what we have is it's benzene. Sorry, it's benzene and toluene, if I remember correctly. Right? Yes, benzene and toluene, right? Okay. So what we have here, it's a benzene mole fraction, right, underneath, from 0 to 1, of course, and the pressure. In this case, in bars, that it's almost atmosphere, right? So if you have, for example, if you have a mixture of 50%, okay, if you have a mixture of 50% of benzene and toluene, right, and you're at this pressure, let's say that it's about 0.3 bars, right? You start climbing, well, you just start augmenting the temperature. Sorry, you start raising the temperature, and this point is going to change until you reach the equilibrium diagram, right? The equilibrium phase. So you're going to have vapor and liquid over here, right? If you see on the right pane, you have a green bar and a blue bar, right? That gives you the proportion, the fraction of each of the phases of liquid and vapor, liquid in green and vapor in blue. The numbers are not very clear, but if you put your mouse on it, you're going to find, for example, in this particular case, that the liquid right now is 96% of the mixture, and that the vapor is 0.034, well, or 3.4%, right? So if you keep rising the pressure, you're going to start having an equilibrium, right? You're going to start having a vapor and a liquid. And in that case, what you need to do to find the different fractions for each one and the proportion, to find the fraction, what you have to do, for example, if you want to find the fraction of vapor, what you have to do is go straight from the point to the saturated liquid line, and then to the molar fraction. So in this case, let me put another date. Let me pick blue. So in this case, would be this, right? This would be the vapor molar fraction, right? And if you do the same thing, but the other way around, you start in the point, in the dot, and you go to the vapor, saturated vapor, you're going to find that that particular vapor has this fraction of benzene, right? So here you have complete separation, but you can have, of course, depends on what part of the diagram you are. You have a lower or a higher amount of vapor and liquid. Right? So this particular diagram let you choose, for example, if you have a mixture, how would be the best way to separate it, right? The highest amount of vapor or the highest amount of liquid depends on it, right? Yep. So that's the pressure and fraction, right? And you can change the temperature. Yes.
So the straight line tells us where that substance is liquid, and the circle one is the one when it's vapor.
Yeah, the blue line tells you where the vapor, what is the liquid, the saturated liquid, right? So if you want to find the concentration of that particular liquid, you have to go from the
at a certain pressure
to the line, to the saturated line, and then find the fraction, right? The same way for vapor, right? For the saturated vapor, you go to the saturation line of the vapor, and then go to the straight down to the fraction of that particular vapor, right?
Okay.
To find these values, the amount of liquid and the amount of vapor, right? You have to do what is called a lever rule that we're going to see in a couple of minutes. Okay, it's more or less well, we'll see it in a couple of minutes. Just let me show you a couple of other things. So the other thing to notice is that what happens if you change the temperature, right? We said that it was at constant temperature, right? Right now it's at 95 degrees. But if you change the temperature, the diagram, well, or the equilibrium is going to start changing, right? Depends on the properties of those particular substances, right? So if you go to a lower temperature, you need less pressure to have a vapor phase, right? If you have a high temperature, of course, it's easier for both components or compounds to go to the vapor phase, right? And if you see the area of the vapor liquid equilibrium, you're going to see that it's bigger while the temperature is larger, right? If we go down to 70 degrees, the area of that particular equilibrium is very small, right? So you don't have too much pressure to work with, right? Instead, if you have a higher temperature, you're going to have more area to work with and to have the correct pressure to have the best separation in that case. Yep. So following the same pattern, if you go to the temperature fraction, you're going to find something that I suppose that you have seen many times, right? Here you're going, what you choose, well, the constant is the pressure, so you can go to 1 atmosphere, right? Or you can go to, in this case, 2.4, right? So it sounds logical that if you raise the pressure, it's going to be more difficult to have a gas or to have a vapor, right? You need to raise the temperature to reach that part of the diagram. If you have a low pressure like atmospheric pressure, you're going to find vapor at lower temperatures, of course, right? It's the same thing as what happens for the boiling point of water in Mexico, right? Water doesn't boil in Mexico at 100; it boils at 94 or something like that, right? Depends on the pressure, right? So if you have a high pressure, you move that line. In this particular case, the area of the equilibrium doesn't change that much as in the pressure, right? But it changes a little bit. Okay. Again, it's easier to you have a higher area if you have a low pressure because it's easier to have a vapor or a gas for a substance than if you have a higher pressure. But in this particular system, doesn't seem that much, right? Okay, so the same thing, right? If you have a mixture, let's say you have this point, you have a liquid mixture, homogeneous mixture that has a composition. Let's say that it is in 0.5, more or less, so half and half. And if you start raising the temperature, temperature, you reach a point where you start seeing the first bubble, right? And that first bubble, of course, is the bubble point, and you can see the fraction of the vapor that you would have, that it's around 0.85 or something like that underneath. And if you keep rising the temperature, you're going to start seeing, well, more and more vapor and liquid, right? You can see these bars, the green bar and the blue bar, how they change, how they behave, right? Depending, and you can see again the different fractions that you have, right? So depending on the mixture that you want to separate or that you want to work with, you're going to find different values, right? Of course, if you have a value very close to the edges, right, almost pure benzene, well, it's very difficult to separate because you can only work with very close temperatures, right? You only have a couple of degrees to have that equilibrium, and the liquid and vapor, they are not going to have, well, if you see the points, so you have around 0.9 in benzene and the other one around 0.95, right? So the fractions are very close together, so you don't separate it very well. For example, a mixture like this one would need, for example, many distillations to be able to separate it completely, right? To purify the mixture. If you have something more in between, right, half and half, it's easier. It's easier to separate because you have a range of temperature that in where you can find different values of mole fraction, right? So in separations, what you have to do is, well, to have these diagrams are very useful, of course, to choose the temperature and to choose the pressure that you need for the separation to be as the best as you can, right? As we did with the three-dimensional, with the 3D model, we have here, for example, we have here only toluene, right? So this will be the boiling point. Here we only have benzene, so that will be the boiling point again, right? The same thing. Yep. So any questions about these particular diagrams?
Teacher, I have a question.
Yes, Diego.
The green bar represents liquid or gas in both diagrams?
So in this case, represent. Sorry, let me close this. Yeah, in this case, represents the liquid represents the vapor. Sorry. You see that?
Okay.
The green line, vapor, and the blue line, liquid. Right?
And in the other one, it was all the way around, right? Like
exactly. They change because, well, you're plotting from lower pressures to high pressures and from lower temperature to high temperatures, right? So it's inverse, right? If you have high pressures, you have liquid. You have liquid, and if you have high temperatures, you have vapors, right? Okay. That's why they seem the other way around. But if you see the color coded, it's the same, right? Vapor, it's always green in either.
Yes. Okay.
Diagram, right?
Teacher, and where can you change the solute? Like instead of benzene, to choose another component?
In this particular app, you can't, right? This is fixed for
just benzene.
Yes, for that particular mixture, right?
Okay.
Because each mixture is going to behave very different. And of course, these diagrams, they only make sense for binary mixtures. Because if not, you start having, well, more. You need more dimensions, right? If you have four different compounds, you need a four-dimensional plot, right? That can be done, of course, right? But it's the same analogy and it's the same equations that you're going to find in activity that you're going to do. You can use the equations to represent a mixture of three components or four or whatever, but to use it like for a plot, they only make real sense for binary mixtures. Yep. I don't know if you have seen that we have diagrams for three mixtures of three components too, right? That they are triangular, and they have again parts of equilibrium for vapor and liquid and so on. Okay, we will see those in another time. Okay. Yep. Any questions about this particular app? I think it's more or less clear. Okay. Remember, if you have anything to annotate, you can go to the participants and put something like that, right? If you need to, that is a useful tool. And of course, if you want to tell me something about the class or anything, you can go to the chat too, and something there, right? Yeah. Okay. So the last step that I want to show you, more to show you a couple of things, is this one, the vapor liquid for non-ideal mixtures, right? In the activity that we're going to do this week, you're not going to work with non-ideal solutions, but it's useful for you to see it. So let me erase this. Okay, so in this particular lab, again, we have the PXY diagram and the TXY diagram. But the other thing that you have is that you have this particular point over here. Let me annotate. You have this particular point, right? I put it in red so you can see it. This particular point. Okay. If you look into the properties, you will see that the concentration of the liquid, if you start in a liquid like this one, okay, you're going to find that that the concentration is going to be the same, right, as the liquid phase. You're going to start in this concentration, and you're going to start raising the temperature, and they don't have an equilibrium in that particular point, right? That's called an azeotrope. So in these kind of mixtures, there is a temperature and pressure, well, a temperature at a constant pressure, where you don't have a change in phases. You don't have an equilibrium. They go straight from liquid to vapor, so they don't change. You don't have any equilibrium at all, right? You just go from like it was a pure component, even if it's not, even if it's a mixture of benzene and toluene. Well, in this case, it's not toluene. In this case, it's ethanol, benzene and ethanol mixture, right? So in that particular mixture, you can have an azeotrope that is this particular shape, and that particular point where at a temperature and a pressure, you don't have an equilibrium. You just go straight from liquid to vapor, right? These kind of mixtures, they're more difficult to separate, of course, because these two areas of equilibrium that you're going to have below, well, at lower fractions for the azeotrope and for higher fractions from the azeotrope, there are smaller areas and they are difficult to separate. Okay? And if you happen to have exactly this condition, this mixture, they can't be separated at all, right? If you have a mixture like this one, what you have to do is, well, add more of benzene, for example, in this case, to have a higher mole fraction, and then to start having a vapor liquid section, right? Yep. So in the activity that I'm going to show you in a second, you're going to do something similar to these diagrams for particular mixtures. Okay. The activity is already on Blackboard. You have to deliver it for next Wednesday, so it's for the whole week, right? And the activity, well, sorry, sorry, I forgot one part. One part is the lever rule. Okay, the app makes it by itself, of course, but this is what you have to do. For example, if you have the diagram and you are in the O point, this point over here. If you are in this particular point, in the O point, right, you're going to have a concentration of W0, right? And you want to find how much of it is liquid and how much of it is vapor, right? So you can find the fractions. You can find the fractions and you can find the amount of it using the measurement of that particular line. So, for example, if you want to find the amount of liquid, you measure. Right. In a second, let me change colors because that one is not good. if you measure this line from the liquid to the O point, right? This is going to give you the amount of solid in this case, because this is a diagram of liquid and solid. It doesn't matter. The amount, the fraction of liquid on that particular solution. So you have the measurement from this point from L to S, right? And if you want to find the amount of solid, right? In this case would be the distance. Let's say that this is the distance LS with bar, and this is the LO with bar. So to find the amount of solid, you would have the distance between L and O, right, with the bar, that it's the distance in centimeters or whatever measure you want to do, divided by the distance of the LS. And if you want to find the amount of liquid, well, it's the same. Well, it's this other point. Let me change color. Use this line over here from O to S, the distance, right? So to find the liquid, you would do the LS distance divided, sorry, the OS. This distance, right? The OS distance. Distance divided by the LS distance. And that will give you the proportion of each of the phases. It happens, it's the same thing for liquids and vapor, of course, right? And if you want to find the percentage, well, it's the same thing as here, right? Yeah, only with the values. If you have the different values, or you can find the values if you have the proportion of it. Either way, right? So that's the level rule. It's useful if you have the diagram. It's if you have a printed diagram, it's useful to use it, right? Any questions about this one? Nope. Sure. Okay. So the last thing that I want to show you, because they at the tech they recommend us to not have classes more than 1 hour, 1 hour and a half through Zoom, because it's start to get boring to see a screen, right? So I'm going to show you the activity that you have to do for this week, right? So the activity, as I say, is in Blackboard already, and in Blackboard here. Okay, so this activity is in pairs. You can do it with a teammate if you want to. It says there are many ways of modeling the vapor-liquid equilibrium diagrams. Sorry about that. In this activity, you will describe and model some interaction. The software that we saw uses some of these models, the apps that we did. This activity is in teams of 2. You must deliver a document, answering questions and doing some problems in Excel. Or if you want to use another software, it's fine, as long as you attach the file and do a little bit of explanation on how you solve the problems in that particular software. Okay, because I don't know all the softwares that there are, right? So please make sure that I can understand the approach with the comments, right? So you have a couple of questions, 5 questions about different laws to model vapor-liquid equilibriums. One of those is the Raoult law, the other one is Dalton's law, and the Henry's law, right? So you have to explain the theory behind it, the considerations that they made, what kind of solutions can be modeled with that particular law, because not all can be defined. And you have to define and give one example of the phase rule and the Duhem theorem, right? The phase rule, I suppose you saw it in mass balance at least. And the Duhem theorem is an addition to that rule, right? And then if you can find how to correct or how to change the Raoult law to have a model, a more comprehensive model, so you can use solutions that are further from the non-ideal, right? Then define what is an azeotrope, what are the characteristics of that particular point, and can we model an isotrope using any of the three laws shown in the second point. Then the vapor liquid equilibrium can be used to separate mixtures, explaining what part of the diagram the system should be and be able to do the separation and so on. Okay, and then a couple of problems, well, a couple of like seven different problems. Those you can find them in the Smith and Van Ness book. I don't know if you have access to it. If not, I can upload it to Blackboard, even if it's piracy, but well, we have an earthquake, so happens. Okay, so I will upload it. So you can have the book and the programs, and you can watch these couple of videos to have more information about how to solve problems and some considerations and so on. If you're fine with watching those kind of videos, those are good for you. Okay, so that's for this session. I don't know if you have any questions, comments, or something that you need to share. If not, we'll see each other next week. This is the activity for this week, right?
Teacher, the activities need to be uploaded right before the class, right?
Yeah.
Okay. Thank you.
So, Luis or Jose? No?
Diego.
The activities are in pairs?
Yeah, this one in particular, it is. We are going to have individual activities, and well, the project, for example, that we're going to work next week is going to be in teams of 4, right? So yeah, it depends on the activity in particular. And remember that I'm going to upload the video of this particular Zoom session to YouTube. You have the link already on the Blackboard. So if you have any, if you want to review some of the materials that we did here, or if you miss a class, for example, I only have 11 participants today, so I know that many people missed this class. So you can watch it on YouTube if you didn't came to the class, right? Yep. Any other questions or something, guys?
No.
No.
Okay, so then see you next week. Have a good week. If you need anything, remember that we have advice sessions on Wednesday and Thursday through Zoom. And well, my email is open for any questions, of course.
Thank you, teacher.
Thank you, teacher. Bye.
Okay, see you guys.
Bye.